In this video, we will be discussing about time and the space complexity. Time and space complexity. Right. So, first of all, we will understand what is algorithm analysis. Algorithm analysis. Algorithm analysis is process of determining amount of resources like time and space read by an algorithm to solve a problem. Any kind of problem you have to solve using resources like time and space by the algorithm. So, when selecting an algorithm, a code should be readable. It means it should be able to be read by all type of coders or programmers of big companies, and it should be a scalable. It means it should work on large amount of data. For example, if my problem size is of 10 integers and my program work for 10 integers, then my program should also work for 1000 integers as well. This is the scalability of my code. Now, talking about efficiency of a code. On basis of time and space, what we can say, a code is efficient if it can use time and space as less as possible. For example, I have two algorithms. One is binary search algorithm and second is linear search algorithm. We all know for any element I have to search in an array. I just have to, in a sorted array, this is for sorted array, I just have to see is my element left of that middle element or right of. If it is in right, I will again go middle of that and see whether it is left or right, and then I will get my element. But in linear search algorithm, for the same, I have to go one by one and then I will get my element. So, we can clearly see this one is more efficient because for million number of data, I cannot go one by one. For million of data, I can simply divide by, I will go in the middle, then I will again go in middle, and then I will again go in middle, and then I will get my element where it is. So, now talking about what is time complexity. So, basically, what is time complexity? It is amount of time an algorithm takes to run as a function of input size. Input size and it shows how time grows with the as input size grows. Grows does not mean increase or decrease. Whether it increase, whether it decrease, whether it is constant, the evaluation of time with that is my time complexity. So suppose I want to search an element in array. So for that, to search, I will write my code as for. I will take a variable. I will start my loop. I will take another variable that will be size of my array, let's say n, and I will go up every updation. I will go one ahead. So if at any time I will get my element, suppose I want to find, suppose this is my array and I have elements 9, 8, 10, 6, 4, 0. Right. Index starting from 0 to 5. Right. So when I will get my x, suppose I want to search 0. Right. When I will get my x as the element, then I can write yes, I have got element, right. I mean here it is a of I, correct. So and then it will break, it will go out of loop, right. So worst case will be I will go and search each and every element one by one going ahead, and at last I will get my element. So for worst case I have to do n comparisons with my x, comparisons. So the time complexity will be order of n, right. Now suppose I have to find 9. So at the first case I will get 9. So the best case to find will be or at order of 1, right. And suppose I want to search 10. So first I will compare with 9, then I will compare with 8, then I will go and I will get my limit. So this will be considered as average case where 3 comparisons I have to do, and this will be of order of 3, right. So generally time complexities are expressed in bigger notations. That is this, right. This example was linear time complexity. So let me draw a graph of this example. Let me draw a graph of this example. Now, drawing the graph, it will be something like here I will plot number of observations. Here here I will plot elements. For every 10 elements, I have to do every 10 observation. For every 20 elements, in my for loop, I did observation of 20 elements. So it will be a straight line graph, and this has a time complexity of order of n, which is worst case in this case. Now, suppose I take another example, binary search algorithm. Instead of linear search algorithm, I will take binary search algorithm. So in binary search algorithm, what we'll do? Suppose I have this array, right? 0, 10, 20. Sorted array. I will first go in middle, see whether my element is at left or right. Then I will again go in middle, and then I will see whether my element is at left or right, and then I will get my element. So for every updation, I have to simply divide my iteration by 2, right? This will be my for loop. So according to this, if I will see it clearly, my time complexity will be order of log n base 2. This will be my time complexity for most efficient code. So when I will draw the graph of binary search algorithm's time complexity, so I will get something like this. On y-axis, the number of observation or operations I will plot, and on x-axis, number of elements, right? Suppose for 10 elements, my value of log 10 base 2 will be 3.3. For 20 elements, my value of log 20 base 2, this is what? Log 2, or here elements. Log elements base 2. For 20 elements, it will be 4.3. This is 4.3. And for 30 elements, it will be 4.9, something here. So for 30 elements, this will be this. And for 40 elements, it will be 5.3, something here, 5.3. This will be a graph like this, right? Less number of operations for same number of elements, less number of operations for same number of elements, right? So you can see time complexity is how time grows as input grows. Time function of n, time is function of n is number of inputs. Time complexity measures the growth rate of an algorithm's execution time as input size increases. If I have constant time, it will be order of 1. Time complexity so thus allows us to compare efficiency of different algorithms. By this I knew that binary search algorithm is more efficient than linear search algorithm. Now, the worst case or the upper bound of an algorithm's time complexity is order of n. This is the worst case scenario. It won't take longer than order of n. So basically any worst case scenario of any algorithm tells us that more time I cannot take than this one. This is the ultimate boundary. Now, there are certain rules for calculating time complexities. So I am trying to write that rules. So, certain rules are there to calculate time complexity. First, if there is constant time operation, for constant time operation, suppose I have to find only one element in my algorithm, then the time complexity of mine will be order of 1. Now, this is generally for arithmetic comparisons and assignments. Second, sequential statements. Time complexity of sequence of statements is sum of complexity of individual statement. Suppose I have a statement 1 and the time complexity of my statement 1 is order of 1. I have a statement 2 and the time complexity of my second statement is order of n. Now, combined time complexity or final time complexity will be order of n plus 1. But this will ultimately become order of n. Why? Because n is a very large number. In algorithm, we have to deal with millions of data. So adding or subtracting 1 does not make any sense. So ultimately I will get order of n. Similarly, if a statement 1 has time complexity of order of n and second statement has time complexity of order of n, we will combine them, we will get order of 2n. This again won't make any difference because there are millions of numbers or data we have to deal with. So basically you can treat n as infinite, you can treat, so infinite plus 1 will be infinite, 2 into infinite will be infinite. Infinite because we have to deal a large number of data in my algorithm. That's why it will also become order of n. Right. When we draw the graph for order of n, for order of n by 2, because for 10 I will have to do my 5 operations, something like this, and 20, this will be order of 2. But ultimately relationship is linear constant. So this difference does not matter. As we saw, we are dealing with large number of data. This is n, right? Now, We ignore constant in bigger notation because they don't change the order of growth. And in competitive programming and software design, distinguishing between different classes of algorithm, example constant G order of 1 versus linear order of n versus quadratic order of n square, is far more important than minor variation in execution speed caused by constants. Now we will calculate time complexity for sum of pairs of given arrays. Right. So I will erase this first. So what will write? Suppose I have an array having elements 6, 7, 3, 2, 1, starting from index 0, 1, 2, 3 and 4. I have to make sum of pair of given arrays. Suppose sum of 6 and 7, sum of 6 and 3, sum of 6 and 2, sum of 6 and 1, and then 7, 3, 7, 2, 7, 1, and then 3, 2, 3, 1, and then 2, 1. I have to make the sum. So the logic will be, I will start from 0th index. I will go up to the last element. I will go one ahead every time. And I will again run a loop in which I will do summation one by one. And then from the second element I will do again summation one by one. This is what my logic is indicating towards. So writing the code, I will be writing. I will go up to the sides. Right. Inside this for loop, I have another for loop that will do my summation. This is what we do for summation, right? This is for I, and this is the j changing, right? This is j changing, and this is the I. So, and one by one, I will be printing whatever I will get, the summation, right? Percentage D, and I will print here sum, right? So, for outer loop, n times the outer loop will run the number of sides. The inner loop, it will run first n minus 1 times, right? For first n minus 1 times, then after that n minus 2 times, then n minus 3 times, and ultimately 1 time only. So time complexity will be outer loop. For outer loop I will multiply, and for inner I will simply, the number of time is n, I will add, this will be n minus 1 plus n minus 2 plus n minus 3 up to 1. This summation can be also written as n minus 1 n by 2. The formula I have used here is 1 plus 2 plus 3 up to n. This gives n into n plus 1 by 2, right? So this will be n, this will be your n square minus n by 2. Now here, since I have added these inside, the outer n does not matter here. So I will simply write order of n square. Constant neglected and dominative term is always taken in consideration. Less dominative term is not taken in consideration. For example, it is something like infinite square plus infinite. So I will consider this term, right? So time complexity is order of n square, right? But if my loop was from 0 less than n and again less than n, right? Here j from 0, then it will be simply n into n, that is outer loop, number of times outer loop, the sizes, and inner loop for inner loop, the number of time the loop runs. Simply it will be n square, right? But in previous case, inner loop was changing, so we added for every iterations, right? Loops, time complexity of loop is complexity of loop body multiplied by number of iterations, right? Conditional statement, time complexity is maximum complexity of branches. Now we will discuss about the space complexity. So I am erasing this out. So a space complexity basically measures amount of time an algorithm uses in relation to input size. So amount of memory used by algorithm in relation to input size. Suppose I have an array of size n, it will take some space, fixed space, to reverse this array. Suppose I have an array, right? And I have to reverse this array. I have to reverse this array. Right. So a space, I will need one more array to reverse, and that array will act as extra space, or what we call auxiliary space. So space complexity is the combination of fixed space and auxiliary space required, or it is a space required or consumed by the program in main memory during execution. That is what we call space complexity. So space complexity will be by n for this and n for this. So it will be still n, right? Now in algorithms, in place algorithm is that algorithm that use constant amount of extra space and have an auxiliary space complexity of order of 1. For example, bubble sort algorithm. Now, what is double sort algorithm? It is a sorting technique in which we consider any first element and then we will exchange it from the last, and by exchanging we do our sorting, right? So this is example of in place algorithm, right? Now, suppose we take an example. Let's take an example of space complexity, of determining space complexity. So I take an example. I have declared an array. I have declared the variable sum, which is 0. This will give order of complexity as 1. This will again give a complexity of order of 1. And I have to do the summation. Right, summation of elements of array, right? Return total. This will again give order of complexity of order of 1, right? So the whole complexity will be order of 1 regardless of size of array, because I have not copied any array and there are fixed number of variables, right? So fixed number of variables, that's why I get order of complexity as order of 1. Now some symbols I will discuss with you. This is omega, best case scenario, for best case scenario. This is theta for average case scenario, and this is bigger notation for worst case scenario. You will denote the time and the space complexity by these symbols, right? This is for today.